In the last video we learned that it is always possible to rearrange the characteristic equation of a system in such a way that certain parameter is isolated from the rest of terms, and that we do that to study the effect of changes in such parameter, in that varying parameter. So, because for each value of the varying parameter, the roots of the characteristic equation are in a different position. So, for example, these positions here. And if we draw all at once all the possible positions of the closed loop poles given by any real v, any v belonging to the set of real numbers, we're plotting the root locus. For example, this could be the root locus of a system, all the possible closed loop poles for any real v. And the name is self-explanatory. We're drawing the locations of all the roots of the characteristic equation, which, as you probably remember, are the poles of any of the different closed loop relations between inputs and outputs to the loop. So another way to look at this is, well, the root locus. The root locus is the set of all possible, all the positions in the complex plane, all the S in the complex plane, for which certain v exists, certain v belonging to the real numbers again, so that v times f of s is equal to -1. This could be another possible definition for the root locus. But notice that this is an equality of complex numbers. It is a complex equation. So we can rewrite it by making the angles and the magnitudes of each side equal. So on the one hand we would have v times f of s, the absolute value of that is equal to 1, and on the other hand we have the angle of v times f of s, but this is just the angle of v plus the angle of f of s is equal to the angle of -1, but the angle of -1 is 180 degrees, or an odd multiple of it, with k equal to 0, plus -1, plus -2, and so on and so forth. Now let's move this term to the right hand side, and we find that the angle of f of s has to be equal to the angle of -1 minus the angle of v, which is going to be either 0 degrees or 180 degrees, because it is a real number. It only depends on its sign. And thanks to that, we can look at these two conditions. But by the way, this is called the magnitude condition, magnitude condition, and this is called the angle condition, So as I was saying, we can look at this in a different way. The magnitude condition is giving us the absolute value of the v generating certain pole, and the angle condition, this is giving us the absolute value of v, and the angle condition, it's giving us its sign. So if the equation is true, there's some v associated to it. Well, the magnitude it can be found with the magnitude condition, and the sign can be found with the angle condition. So according to that, we can define the root locus again, the root locus, in a simpler way. Just let me write it. The root locus is the set of positions in the complex plane satisfying the angle condition. This is the key point, because for each of those points there's always certain v also satisfying the magnitude condition. Now let's continue by recalling that f is a rational function, f of s, this f of s here. So it has a numerator and a denominator, or in other words, it has some poles and some zeros, and we can find those poles and zeros, and then we can rewrite the function like this capital K as apart from s plus z1 times s plus z2 and all the rest of binomials defining the zeros over s plus p1, s plus p2, and all the binomials associated to the poles. So according to this, we can rewrite the magnitude and the angle conditions like this. The angle of v times k times, okay, let me copy and paste the angle, the magnitude of this magnitude is equal to 1, and the angle of this is equal to the angle of -1 minus the angle of v. But the angle condition, which is the one defining the root locus, we can work on it, because this, by applying the properties of the complex numbers, is just the angle of k, of capital K, plus the angle of s plus z1 plus the angle of s plus z2 plus all the other angles in the numerator minus the angle of s plus p1 minus the angle of s plus p2 minus all the rest of angles given by the poles. And this is the angle of -1 minus the angle of v. Now let me take this angle here to the other side. Okay, minus the angle of k. Very good. We have all the real terms in the right hand side. And now let me call this angle here phi1, and this one is going to be phi2. All the angles given by zeros are phi, and this is theta1, and this is theta2, and all the rest of angles given by poles are thetas. And this is equal to, okay, this is minus 100. No, we don't need a minus. This is 180 degrees, or any multiple, odd multiple. This is plus minus either 0 degrees or 180 degrees, and minus again 0 degrees or 180 degrees. It depends on the signs of V and K. Okay, now let's see the graphical interpretation of this equation. All these angles phi and theta are, what are they? Well, let's suppose we have some certain positions for the open loop. Remember, open loop poles, and I don't know, open loop zeros. I will only use real ones in this case. So let's see if this point satisfies this equation. Let's see if this point belongs to the root locus. Well, this angle is in the picture, this angle here, phi1, because this is the position no, sorry, this angle is theta1, because this position is minus p1, and this angle here is theta2, because this is the pole minus p2, and this angle here is, since this pole is minus z1, this angle is phi1, and if there's some other pole, well, this angle would be phi2. And the same would happen if we had zeros or complex zeros and complex poles. This is very easy to see because these lines here are these binomials in the equation. But in any case, the sum of all those angles can add up to an to odd multiples of 180 degrees. So minus 180 degrees times k, but for k equal to 135, and that happens when the sign of v is equal to the sign of capital K, when we have either this case or this case. If all those angles add up to an odd multiple of 180 degrees, we say that this position is in the root locus, but specifically in the positive root locus. And if those angles add up to even multiples of 180 degrees, so in this case k is equal to 0, 2, 4, and that is something which happens in either this case or this case. So when the signs of v and the sign of v and the sign of k are different, when those two signs are different, well, in that case we say that the point is in the negative root locus. So according to this, we could draw the whole root locus by checking each position of the plane. We can apply the angle condition here, and the angle condition here, and the angle condition here, and I don't know if in this condition the angle is fulfilled. Well, then we know that there is certain v associated to it, and that for that v the characteristic equation is 0 when s is equal to this position here, or actually minus this position here. But in any case, this v, its sign is given by which of these two cases we are in, and its absolute value can be found directly by applying the magnitude condition. So as I was saying, we could check all the positions, and in doing so we would be approaching the root locus. But if we want to distinguish perfectly which points of the complex plane are part of the root locus and which aren't, this procedure would take us forever, because there are an infinite number of points in the complex plane. Instead, we can use the rules for constructing the root locus that Evans developed. With them, we can sketch the root locus in a simple and straightforward manner. And that's what we'll learn to do in the next video.